Mercury, the smallest of the rocky planets, the closest to the Sun, and the fastest traveler in our solar system. On the surface, it seems unremarkable. A hot, airless rock, scarred with craters, bathed in solar radiation. But beneath that unassuming shell lies one of the most fascinating orbital mysteries in all of astronomy. Mercury doesn't follow the rules the way other planets do. Its path around the Sun is not just elliptical, it's highly eccentric, meaning its distance from the Sun changes drastically during each orbit. Its inclination is steep, its motion is quirky, and, perhaps most famously, its orbit refuses to behave in a way that classical physics can fully explain. This anomaly once stumped scientists for decades. It challenged Newtonian physics, confused astronomers, and ultimately led to one of the most revolutionary breakthroughs in human history: Einstein's general theory of relativity. In Mercury's orbit lies a cosmic story, a story about gravity, time, and how even the tiniest planet can unlock the deepest secrets of the universe. At a glance, Mercury's orbit is just another ellipse. But dig deeper, and things get strange. Mercury's orbit is the most elliptical of all the planets, ranging from about 46 million kilometers to 70 million kilometers from the Sun. That means the Sun looks nearly twice as big in Mercury's sky at perihelion than it does at aphelion. Even stranger is Mercury's 3:2 spin-orbit resonance. It rotates 3 times for every 2 orbits around the Sun. This leads to bizarre patterns in day and night. A single solar day on Mercury, one sunrise to the next, lasts 176 Earth days, which is longer than its year. If you were standing on Mercury's surface, you could watch the Sun rise slowly, pause in the sky, move backward, then resume its path. Time, here, bends in ways that defy our earthly instincts. In the 19th century, astronomers noticed something odd. Mercury's perihelion, the point in its orbit closest to the Sun, was shifting over time. This is called perihelion precession. Some of that precession was expected. Other planets, especially Venus and Jupiter, tug on Mercury gravitationally, causing its orbit to shift. But even after accounting for all known effects, there remained a discrepancy, a tiny, unexplained drift of 43 arcseconds per century. Tiny, but persistent, and troubling. Some scientists proposed there was an undiscovered planet inside Mercury's orbit, dubbed Vulcan. Others wondered if Newton's laws simply weren't enough. The mystery remained until 1915, when Albert Einstein proposed something bold. Gravity is not a force pulling bodies together. Instead, mass bends space and time, and objects follow those curves. Einstein applied his new theory, general relativity, to Mercury's orbit. The math was clear. The precession? Explained. Perfectly. Mercury's orbit became the first experimental confirmation of Einstein's revolutionary view of the universe. Today, Mercury serves as a gravitational laboratory. Because it orbits so close to the Sun, where space-time curvature is strongest, it allows scientists to test relativistic effects in ways no other planet can. Even the tiniest deviations from Newtonian predictions show up more clearly in Mercury's data. Spacecraft like NASA's MESSENGER and ESA JAXA's BepiColombo use sophisticated instruments to measure the planet's position and motion with incredible precision. These missions help refine our models of gravity, planetary formation, and orbital mechanics. In studying Mercury, we're not just understanding one planet. We're learning how the entire fabric of reality works. Over long timescales, millions or billions of years, Mercury's orbit is chaotic. Not chaotic in the sense of disorder, but in the precise, mathematical sense. sensitive to initial conditions. Small changes can lead to drastically different futures. Computer simulations suggest that over the next few billion years, Mercury's orbit could stretch further. Its inclination could shift. In rare scenarios, it might even destabilize, potentially colliding with Venus or plunging into the Sun. These are low-probability outcomes, but they reveal something sobering. Even the solar system, which feels eternal, is not guaranteed to stay the way it is. Mercury reminds us that the universe is dynamic, not static, that orbits evolve, that even the most ancient systems can drift. There's something deeply poetic about Mercury's strange orbit. Here is a planet that resists the tidy paths we expect, a world that challenges neat models and smooth curves. Its orbit is eccentric, irregular, hard to predict. And yet, that orbit is real. It's governed by laws deeper than we can see at first. Isn't that, in a way, like life? We expect symmetry, simplicity, predictability, but we find instead complexity, change, tension. We find paths that wobble, turn, and surprise. We live in orbits shaped by forces seen and unseen, emotional, gravitational, historical, philosophical. Mercury becomes more than a planet. It becomes a mirror, a metaphor for how truth often hides in the anomaly, for how discovery comes not from what we expect, but from what refuses to fit. For the ancients, Mercury was a god, Hermes to the Greeks, Mercury to the Romans, a messenger, a trickster, the only god who could move between worlds, from Olympus to Earth to the underworld. Fast, elusive, brilliant. Perhaps it's no coincidence that the planet Mercury behaves the same way. It appears only at dawn or dusk, always near the sun, never high in the sky, difficult to spot, fast-moving, flickering in and out of view, a celestial symbol of the boundary between light and dark, known and unknown. And just like the myths, Mercury's orbit blurs the lines between realms, between classical and modern physics, between chaos and order, between what we know and what we're still learning. In fact, the more we study exoplanets, planets around other stars, the more we find Mercury-like worlds, close orbiting, tidally locked, eccentric in motion. Some orbit red dwarfs. Others whip around their stars in just a few days. Many are scorched, iron-rich, and dense. In that way, Mercury becomes a prototype, a case study for understanding rocky worlds across the galaxy. And as we continue to explore, we realize how rare Earth is. A planet with a nearly circular orbit, a stable climate, a moon that steadies its tilt, conditions that support life and have done so for billions of years. Mercury shows us not just what other planets are like, but what they are not, and how precious our own orbit is. The Bepi-Colombo mission, currently en route, will arrive in the early 2030s. It will orbit Mercury with twin spacecraft, studying its magnetic field, internal structure, and surface composition. It will track Mercury's orbit with such accuracy that we may detect even more subtle deviations, ones that could hint at new physics. And perhaps, Mercury has more secrets to share. It may help us test theories of dark matter, or reveal clues about the sun's long-term evolution. It may reshape our understanding of how rocky planets form close to their stars, not just here, but across the Milky Way. And in doing so, Mercury continues to serve its ancient role, a messenger between realms, between the past and the future, between mystery and understanding. Mercury's orbit is strange, unruly, brilliant. It puzzled Newton. It proved Einstein. It speaks to chaos, to chance, to the delicate balance that holds the solar system together. And it reminds us, In its stubborn deviation, that truth often hides in the margins, in the irregular, in the orbit that doesn't quite fit. In Mercury's path, we see not just gravity, but beauty. Not just math, but meaning. A message written in motion across 4 billion years of time.